Okay, in this video I want to talk about chapter 7 in your book. That's Newton's third law. You've heard it in many ways. You've heard it mentioned before. Of course, action, reaction. We're going to look at it a little bit more, probably more in depth, more analytically. And we're not going to do any problems today per se. That'll be in the next lecture. That'll probably be Friday that we're doing. Unfortunately, this will probably get released Thursday night. You may not watch it before the lectures. Do if you can. But I'm going to do it so that you don't have to watch this 7.1 to 7.3 to do 7.4, 7.5. I'll talk about that on Friday. But I want to talk about Newton's third law. Newton's third law. Basically, you've seen it before. 7.1 talks about interacting objects. Interacting objects. Now, when objects interact, if I hit the wall, that's me hitting the wall. There's an interaction when I hit the wall. My hand hurts. Right? Hopefully, make the wall hurt a little bit. Yeah. But let's look at the forces involved. So when I hit a wall, if this is the wall, I'm exerting a force on the wall. Make this the wall. Do it like that, so you know it's rigid. But the wall is also, this is the force of the hand. The force of the wall is in this direction. It didn't keep moving. It stayed there solid. I am not Superman or whatever Marvel character you want to pull out of some obscure Marvel series of 1960 and put in a movie and hopefully it makes money. No. It stays there. So if it stays there, it's going to exert, I put a force on the wall, but the wall puts a force on me. This is known as an action-reaction pair. Action-reaction pair. Now, we'll get into how this affects things here in a little bit. The book goes into kind of honestly a little more detail than I like on 7.1 and 7.2 about these action-reaction pairs. What I'll just say, what's important to know in these action-reaction pairs, basically here's a system. And here's the environment. So this is like the classroom, and that's the world around you. Okay? So what you're going to be interested in is there's going to be internal forces, external forces. These external forces are external to the system. And you're going to wonder about how they interact. Because they're going to interact. Okay? They're going to interact. Now, internal forces, what I want to say, and this is a little bit ahead, but I'll say it anyway. Internal forces don't move objects. External forces move objects. By move, makes them accelerate. Changes their motion, I should say. Alright? Changes their motion. That's what forces do. Newton's second law, they accelerate objects. They change their motion. So let's get an example of this. Okay? If I am floating in the air. I'm weightless. I would love to be weightless. In space, weightless would be an awesome feeling. And I do this. Am I going to go forward? And I'm weightless, floating? No. Because what am I pushing against? There's nothing. If you've ever been walking on ice, if you walk on ice, can you move forward? Your feet go out from you. Maybe you fall down. You can't go forward on ice. If you go skating, that's why, skates and stuff like that are different. You walk on a skating rink surface, it's hard. You have to kind of dig into the ice to get across it. There's no external force to make you move. Internal forces don't move objects. Say a guy had a boat. Here's the classic example. He's got a boat. And a guy's sitting in the boat. And what's he got holding in his hands? He's holding a fan. And what's he doing with that fan? Well, he's taking that fan and here's the sail. So he's holding the fan and the fan's blowing into the sail. Will he move? The answer in this case is no. Because the force making him move, this wind from this trying to go in, is internal to that system of the boat. If the wind comes from outside the boat and hits that sail, he'll move. But if the forces are internal to the system, they're not going to change the motion of the boat. If I walk and can't get traction on the ground, I ain't moving. When your car's on ice and you're trying to move and it just sits there and spins out, there's no forces external to the car working on it. Actually, the friction between your tires and the road, that frictional force is actually what pushes you forward. That helps you move forward when you walk, when you're in a car, your tires on the car and the road. That's what makes you go forward. Because those are external to the car, to you as you walk. Okay? All right. Interacting objects. That's pretty cool. All right. Now, the question becomes, I'm going to move this ever so slightly. Hopefully my phone doesn't fall. Okay. Now, for interacting objects, in 7.2 is about analyzing interacting objects. Analyzing interacting objects. I'll say you need to do, trying to summarize that is, draw free body diagrams. FBD is okay with me. So you draw an FBD, a free body diagram for each system involved. You want to do a free body diagram for each system involved. And they use one in the book, somebody pushing a crate. So if you're pushing a crate, this could be, let's not do push a crate. Let's do pulling a dog to the vet. Veterinarian, not veterans. So pulling a dog to the vet. So the picture would be, here's the guy. He's got the leash, he's grabbing hold of the leash. Leash is to the dog. The dog does not want to go. He's sad. It's his ears. He's not pointed, he's not a Doberman. He's sad, and he's trying to go that way. The guy's trying to pull him back the other way. And the guy's like, "Urgh." He's trying to pull his dog to the vet. Now, so let's do a free body diagram for each one of them. Okay? So let's do a coordinate system. to use red for this. So for the man, here's a dog. D-A-W-G, dog. That's how we say it in the South, right? Yo. All right. So for the man, of course, his weight, so you got gravity pulling down on him. Normal force from the ground pushing back up. Now the dog's pulling this way on him. This is the force of the dog. But what's that action-reaction pair? And that is the force of the man. We'll make this dog on man. This is the force of man on the dog. And we'll say here, just to specify, we'll say no motion. It could be with constant motion. We'll say there's no net motion here. It's a standoff, right? Dog's going this way, he's going back the other way. So this is for the man, that's his free body diagram. For the dog, and we'll label this as the weight of the man. So the dog here, you got D-A-W-G, dog. You got the normal force. Here you got the leash, so the man. Here the force of the man on the dog. And this is the force of the repair from that, of the dog. Pull on the man. And I'm sorry if that's, my green is going out. Let me see if I can get the trash can. Missed. Dang it. So this is the force of the dog on the man. You pull it on it. Okay? So what you notice is this one here, what the book says, what you've got is the paired up with this one here, because they're the same. They're the action-reaction pair. Because these action-reaction pairs are equal. Something I didn't say earlier, but I will say it now. Action-reaction pairs of forces are equal. Okay. Pairs are equal. All right. So let's go back. I'm going to push the cart the other way. Oh. See, this works. Hope it works. Check back here. Yeah, that works. Okay. They talk about propulsion in the book, because that's kind of a special action-reaction pair, propulsion. How does a rocket work? Well, of course, that could be for a rocket. That could be walking. You walking as an example of propulsion. And a car moving. So for propulsion, you've got to have the outside action-reaction pair moves the object. It moves that object. So for a rocket, here, black motor, black smoke coming out, right? Now, what happens? What's going on? This internally, it's sending out hot gases at, honestly, like, what are these? 1,500 to 2,000 degrees Celsius. It's sending those things out the back end at Mach 1, sometimes even faster than Mach 1. Lots of times faster than Mach 1, I should say. So there is a force. So it's pushing out this way. So you got a force of the motor down. Force of the motor on the flame, let's say. Or on the, we'll call it hot gas. On the particles. That's better. Really, hot gas particles. It's all that force. It's shooting it out the back. Shoot all that flamage, hot gas, and particles out the back end in that smoke. Well, for that to occur, there's got to be an action-reaction pair. And that action-reaction pair, then, is the force on the rocket from the hot ejected material. The hot ejected material is what pushes the rocket forward. You shoot it out fast out the backside and makes you go forward the other side. Okay? You've seen the guys with fire extinguishers and stuff. You might have saw Wally. If you remember that movie, when he was trying to with Eva. He was seeing they were in space and they're floating. She can move around and he's having to get the fire extinguisher and kind of going back and trying to follow her around. Well, the fire extinguisher goes one way, he goes the other. That's the way Wally did. And the physics was pretty good when they did the stuff. If you remember the movie The Martian, at the very end, when basically, what's he do? He basically puts stabs his glove, so his internal air, and he uses that kind of like, Iron Man or whatever, using that to push himself forward. As the gas comes back, he goes the other way. Now, I thought what was really cool in that movie is what's called center of gravity. We'll learn that's where you rotate from. If you do this, you're going to start spinning yourself around. So you do spin yourself around, and he would go forward. But that's much harder to do than it looks in the movies. Let's just say that. The reality is. So actually, Martian did a decent job with that physics. So rockets, that's how they work. The force pushing out the gas, the reaction pair from that pushes the rocket forward. For walking, it's a zombie, right? Oh, they got zombie here. There's fresh meat over here or something. So the zombie's walking, and that's his feet. Here's the surface. So as the zombie walks, his feet, if you think your feet push back, this is the direction of the force of the foot on the ground. Force of the foot on the ground is back this way. The ground itself. So if it doesn't get out of the way, if like sand is one thing, but the ground itself pushes you forward. It's an action-reaction pair from that interface of your shoes to the ground. So what makes them go forward? The force of the ground on the foot. Action-reaction pair. Now think about sand when you're walking at the beach. Sand is not real stiff and sturdy. So as you're walking, especially in loose sand, your foot goes back a little ways. Is the action-reaction pair as big in magnitude? No, it's less force. So to do the same thing at the beach, you got to exert more force to go forward at the same rate. That's why if you walk in the little loose sand part of the beach and you walk a mile in that, you get darn tired. Or I'm sorry, in the south, you get tarred. Okay, not guitared, but get tarred. Yeah. All right. So that's the force of the ground on the foot when you're walking. For a car that's moving, you think about the tire. So the car, to move forward, is going to have the road, we'll say forwards that way. It's going here. So at this interface, right here at this interface, the car on the ground, and if you're behind the car like on gravel, it'll spew gravel out behind you, 10, 20, 30, 40 yards on a gravel road or something. So it's actually exerting a force this way of the wheel on the ground. Well, that's the force of the wheel on the ground. force, the reaction pair for that is the ground on the wheel. And that force of the ground on the wheel helps you go forward. If you spin out, if you floor it and it starts going, it starts making smoke behind you, like I used to do with my old Mustang, a little bit anyway, you don't have traction. So do you go forward? No, because the friction between that wheel and the ground there isn't enough. If you're on ice, I got my dad's old pickup, his old Toyota pickup. I had a trailer behind it. I backed in the yard, trying to go back out, put it by the barn. Well, that truck in the yard, because it was wet in that grass, lighting it back in on the truck. It kept spinning, and I'm like, oh crap, I'm gonna have spin out places where mud and crap in the yard. So I had to mess around and get out a different way. There wasn't enough friction. The ground couldn't push me forward. It was wet, and the dirt was loose, and so it just couldn't hold there to do an act. What little force it could do wasn't enough to move that little truck forward. Okay. That's propulsion. That's the way propulsion works. We want things move. Action-reaction pairs. External to the system, ground on the foot, ground on the wheel, rocket from the hot ejected material. All these forces that make it move are external to the rocket, the zombie rocket, and the wheel rotating. Okay. Now, let's look at Newton's third law in itself. Okay. Now, Newton's third law itself, this is section 7.3. Newton's third law basically says for every action, there's a Jackson. No, that's action Jackson. For every action, there's an equal and opposite reaction. Equal and opposite reaction. Get this out of here and not make a mess. So what is that saying? The action-reaction pair must always occur. So there's always going to be an action-reaction pair and be equal in magnitude. In other words, the same value, the same amount of push or pull, but opposite in direction. Every time there's a force, there's another force with it, an action-reaction pair force that you've got to take into account. And Newton came up with this in the 1600s. Goodness, that boy was smart. He was pretty sharp. But of course, as Newton said, if I've done anything, it's from standing on the shoulders of giants. That was a famous quote of Newton. And these giants were, of course, Newton, or Galileo, Copernicus, other guys that did a lot of good work. And for Newton, being that magnanimous was strange because Newton was full of himself. Conceited, be a word we would use nowadays. He was full of himself. But, when you advance science more than anybody in the modern world, as far as we know, since science has been developed, probably 5,000 years before Christ to now, Archimedes, Newton, Einstein. Newton advanced science more than Einstein did, just being honest with you. Now, Newton, we'll see it over time, but Newton was amazing. He truly was, and the way he changed the way we look at science. Now, this reasoning with Newton's third law, let's think of it like this. All right, here is the earth. It's a happy earth. walrus. That's not a walrus. What is that? I know what we can make it. It's a UFO. UFO. It's an alien. It's an alien. Of course, if aliens answers, you better have incontrovertible evidence. But we'll assume this is an alien. And what's the Earth? He's saying, hey, I got me a visitor. I hadn't had a visitor in a long, long time. So he is, gravity, he's always, the Earth is very attractive. It's a very pretty Earth. Don't believe me, look at it. It's also attractive because of gravity. So the Earth's going to be pulling the UFO down to it. This is the force of gravity on the UFO. But for every action there is an equal and opposite reaction. Does the UFO have to exert a force on the Earth? Yes, it does. So there's actually a force of the UFO on the Earth. And these forces have got to be equal. These forces have got to be equal. So if they're equal, why doesn't the Earth move? When there's satellites going around us, when we drop things, satellites come crashing down, they're pulling on there. Why doesn't the Earth move? Anybody? I'm waiting. Oh, no, I'm Zoom. I'm sorry, I forgot. It doesn't, because how much mass does UFO have? It better be like that one in Independence Day number 2. When I say Independence Day number 1, those were big honking UFOs. Independence Day number 2 was huge. It could spread across the Atlantic Ocean. Because if it's not, the mass of the Earth is so great, it is so great, that could it pull the Earth very much? No. Now it is pulling. It is pulling, so let's do that. Let's take, so the force of FG on the UFO equals force of the UFO on the Earth. Well, if that's true, then this would be the mass of the UFO, acceleration of the UFO. This would be the mass of the Earth. We'll just do E. Make it easy. Acceleration of the Earth. So, let's see if I can find the acceleration of the Earth. Accelerating Earth, we'll bring this over here. Acceleration of the Earth, and I just switched it and moved this over. And divide both sides by mass of the Earth, would be mass of the UFO over mass of the Earth times the acceleration of the UFO. Now, acceleration of the UFO might be pretty big. But what about this ratio here? Mass of the UFO over mass of the Earth. Mass of the UFO over mass of the Earth. What's that going to approach? I hate to jump in the limit and all that stuff. But no, what's it really going to approach it? What is it? Are they basically the same? No. Earth is so much bigger. So if Earth is big, 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 this is just big. But big, 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 10 to the 24th, big, big, big. And this may be 10 to the 5th, 6th, 7th, 8th big. It just annihilates it from the bigginess of the Earth, right? So if this is really, really big over a number a lot smaller, this approaches 0. So if it approaches 0, I'll put approaches here. Then the acceleration of the Earth approaches 0 as well. So when a UFO goes by and we capture it, or if an asteroid goes by and we capture it, does the Earth move? No. Now if it was really big, it's a different story, right? And so tractor beams, let's think of tractor beams. The old tractor beams in Star Trek and Star Wars and Star this and Star that, whatever. Star memes, I don't know. If you got a tractor beam, you send out a beam and it pulls you to it. Well, a tractor beam, If something's pulled to you, you're going to be also pulled to it. Now, if you got a lot of mass, it's okay. I mean, you'll just move a little bit, and it'll move a lot of bit, right? Like that, a lot of bit, little bit, because of the mass difference, just like the Earth and the UFO. But if you're trying to use a tractor beam on something that's about the same size, you both are going to meet in the middle. Okay, you're going to meet pretty close in the middle if you're the same mass, same size. Well, same mass, I should say. Now, so, maybe the physics of tractor beams on Star, the Star Wars, Star this, Star Raiders, Star Fighters, whatever. Now, I will say this. This effect, though, works for circles as well. Say we have, we know all the orbits are actually ellipses, but as the Earth goes around the sun, it's a little closer to one spot, a little further away on, say, the other side. What are we doing to the sun? When we're farther away, we don't have as much gravitational force. It doesn't move as much. When we're on the other side, we got a little more, we're a little bit closer, and so it pulls us a little bit more. So as we orbit around the sun, we make the sun wobble. Okay? And that wobbling of the sun has a pretty interesting effect. Now, for us on the Earth, it don't mean anything hardly. Not really that much. But say we were looking at a star way out in the sky. 50, 100 light years away. Light years, how far light can go in a year. Put it this way, think about it. Light can go from here to the moon in about, second and a half or so. So if light can go from here to the moon in a second and a half, light goes from the sun to us, 93 million miles, in about 8 minutes. Okay? 7, 8 minutes, about 8 minutes. So how long can it go in a year? Well, the nearest star is Alpha Centauri. That's 4 light years away. You can see how long, and the numbers get in the tens of the 20s and stuff, right? For miles. Miles is irrelevant. That's why they use light years. But say there's something 50, 100 light years away. It took light 50 years to get to us. We can image that with a telescope. And we now can make our telescope so precise, looking at that image of the sun, we can actually detect if the center of that dot where that star is, if it moves a little bit. And if it moves a little bit this way or that way, something's got to cause it, right? You remember we talked about forces and agents, and every force, something's got to cause an agent. If something's changing its motion, something's got to cause it. Well, we make the assumption those are planets. I don't know. Maybe God's doing this. I don't know. But we assume it's planets. And if it's a planet, based on how much it wobbles and how fast it wobbles and the amount of the wobble, we can actually tell the orbit of the planet. We can tell how long it takes to go around it, how long a year it is on that planet. We can get an idea of how far away it is from that star. And that sort of information is really, really interesting. We can see, by looking at wobble of stars, because of Newton's third law. Now, it's circular motion, but it's the same idea. Closer here, it's going to be attracted more further away, less there. By Newton's third law, that wobble of action-reaction pairs causing that wobble, which ain't much, but it's enough. We can actually see the effects of other planets, and we can postulate the planets that are around it. Now, some of you may be saying, well, that doesn't work for little planets like the Earth. Not yet. We're getting better at it. They're getting more precise techniques on it. It's harder to see things the size of the Earth. It's easier to see planets the size of Saturn and Jupiter, stuff like that, especially if they're close in. But we're still looking for planets. One of the ways is action-reaction pairs. Okay? One thing the book tries to say is just because two things interact, notice in this case, they have different direction of their accelerations. There's something, you can set up a situation like this where this is a pulley. And let's put an object right here and say an object right here and tie them together with a rope. And if you do that, we'll analyze this a little bit more. And this has got some mass. This has got some mass 1, and this is some mass 2. So gravity's pulling down on this. So gravity's pulling down on that. The tension in the rope, is pulling up. But that means there's a force this way, a force of gravity here, and we would say a force of friction this way. And then there's a tension force up here. And we'll analyze this situation. And from this, we can determine the acceleration. But notice, acceleration here for this system is in negative y direction. Here, the acceleration for this system is in the positive x direction. So ropes will learn just redirect forces. Ropes and pulleys can be used to redirect forces. Okay? All right. This is about enough to do section 7.4. Once you understand it, ropes and pulleys, and then some more examples of interacting objects. We'll do that on Friday, and that's the first 3 sections in chapter 7.